All right, so good morning, everybody. So today's October the 18th. A couple things to talk about here at the beginning. I want to start talking about next week and how things are going next week. So we'll have live lecture on Monday, as usual. Next week, we're talking about inverse functions next time. With what we're talking about today and on Monday, I want to remind everybody that those are on exam 3, those topics. So as you're looking at this stuff here at the end, rational functions will be on exam 2. That's where exam 2 is going to finish. Combining functions in function composition will be on exam 3. And what we talk about next Monday will also be on exam 3. Those topics will not be on the exam next week. So next week, we're headed into a test week, so we have a little bit different schedule. Monday, we'll have live lecture, like I just mentioned. Wednesday, no live lecture next week. I will be on campus next week, Tuesday and Wednesday. My Tuesday office hours will be 4 to 6 in the afternoon, and my Wednesday hours are a little bit iffy right now as far as when they're going to be. On your calendar, I have it from 9 to 11, but I believe that's not going to work out for Wednesday. And so right now I'm looking at approximately 11 to 1. And I'll email everybody about that through WebAssign and give you a better idea of when I'm going to be in my office on Wednesday of next week. The testing window for exam 2 opens next Thursday and runs through the following Tuesday, which is Halloween, so October 26th through October 31st. So the exam review, the exam 2 review is up. It was up earlier this week. A very good review, just want to point out, and lots of, in this case, there's no problems out of your textbook with problem numbers and everything. These are all problems that I've put together myself for the review. And all the solutions are on the review also on a separate document. And so I've actually uploaded 2 files for the review. So please start working on that review. And as you get through this weekend and everything, that should kind of be your primary focus, is finishing up any WebAssign homework that you've got due and then getting ready for exam 2. Online office hours, I'll have online hours this evening from 8 to 9 o'clock, tomorrow from 11 to noon, and then next Sunday and Monday, so the 22nd and the 23rd, I'll be in my office in the evening also. And then I won't have online office hours the rest of the week because I'll be on campus on Tuesday and Wednesday. So just a little bit, I just wanted to go through a little bit of a heads up of what we're talking about there. So, all right, so today what we're going to do is we're going to have one last look at rational functions. I'm going to look at one more example to kind of wrap all that up from what we did in class, in lecture on Monday. Finish that up, and then we're going to start gearing ourselves towards exponential and logarithm functions. But before we talk about exponential and logarithm functions, we have to talk about function composition and inverse functions. So those 2 topics are required before we deal with exponential and logarithm functions. So it kind of looks like, why are we all of a sudden talking about function composition and inverses? Because it seems kind of out of place, but those are both directly geared towards dealing with exponential and logarithm functions, which is our next really big goal, and we'll start that right after exam 2 is over. All right, so one last look at rational functions. So we're going to start off with an example, or not start off, but we're going to work through an example of a rational function. Remember, a rational function, whenever your algebra teacher's talking about rational functions, they're talking about a function that's a fraction, and it's a fraction that's a polynomial in the numerator and a polynomial in the denominator. So let's say we have this function, x minus 2 over x squared, let's say plus 2x minus 8. And And then in the numerator, I'm going to make that an x plus 2. So we have x plus 2 over x squared plus 2x minus 8. So a typical example of a rational function. Now, first thing you should do is factor anything that factors. So in this case, the denominator factors x plus 4 times x minus 2. All right, and then remember, there's this list of things that I'm going to ask you to find for any rational function. And this is what you should expect next week on the exam also, is that I give you a function, and this is the list of things that I'm going to ask you to find, right? And remember, this is the list. Vertical asymptotes, horizontal asymptotes, x-intercepts, y-intercept, and then the graph, making a rough sketch of the graph. Okay, so the vertical asymptotes. Remember that to find the vertical asymptotes for a rational function, and to remind you from last time, what we're doing is we set the denominator equal to 0. And wherever the denominator is 0 and the numerator is not 0, then you're going to have a vertical asymptote, because that's a break in the domain. That's a restricted value. It's a value that's not in the domain of the function. So in our problem, notice there's no common factors between the numerator and the denominator, so we're okay that anything that makes the denominator equal to 0 is going to be a vertical asymptote. And so the vertical asymptotes in this problem would be x equals negative 4 from the x plus 4 in the denominator, and x equals 2 from the x minus 2. And remember, what we're doing is we're setting the denominator equal to 0. And so technically what we did is we took x plus 4 times x minus 2. We set it equal to 0. And you just get each factor equals 0. And you end up, you get these solutions. And so that's why those are the vertical asymptotes, at negative 4 and at positive 2. All right, the horizontal asymptote. Now remember, with the horizontal asymptote, what we talked about doing is we talked about looking at the terms with the biggest powers in the numerator and the denominator. Because what we're doing here is we're looking at what happens as x gets big, as x goes to infinity. As x gets to be a bigger and bigger number, the only terms that matter in the numerator and the denominator both are the terms that have the biggest powers on them. Those are the terms that control the numerator and the denominator. So in this case, this would be x over x squared. That as x goes to infinity, y is going to approach x over x squared. Notice all the other terms don't matter as x gets larger and larger. And what happens there? The x's cancel and you're left with 1 over x. So y is going to 1 over x, but x is getting to be bigger and bigger and bigger. And so as x gets bigger and bigger, 1 over 10, 1 over 100, 1 over 1,000, and so on, right? The denominator is getting bigger and bigger there. What's happening? Those fractions are getting closer and closer to 0. And so the horizontal asymptote here is at y equals 0, or the x-axis. Always remember that in this situation where the degree of the numerator was less than the degree of the denominator, the degree of the numerator is less than the degree of the denominator, this is always going to happen, that you have a horizontal asymptote at y equals 0. Right, when the degree of the top is smaller than the degree of the bottom, then you're going to automatically have a horizontal asymptote at y equals 0. All right, then the intercepts. All right, so the x-intercept. So remember that the x-intercept is where the numerator is equal to 0. So you set the numerator equals 0. And so in our problem, the numerator is x plus 2. You set that equals 0, and you get negative 2. And so we have an x-intercept at negative 2, 0. And then the y-intercept, there all you're doing, remember, is you are setting x equals 0 every place you see it in the equation. So when you set x equals 0 in the equation, you get y equals 0 plus 2 over 0 squared plus 2 times 0 minus 8. And so you get y equals negative 1 over 4. All right, so that's our y-intercept is at 0, negative 1/4. All right, and so now what we want to do is try to put this information together on a graph. All right, so I'm going to make a sketch of the graph over here, or put it over on this side. Going to get a little bit more room on the negative side than the positive side because that's what we'll need. And then draw in the things, first of all, that you've already found. So I've got a vertical asymptote at -4. So here's a vertical asymptote at x equals -4. We have another vertical asymptote at +2. So here's another one at +2. We have a horizontal asymptote on the x-axis. So I'm going to put a dashed line just a little bit above the x-axis only because I want to see it. But we have a horizontal asymptote at y equals 0 right there. We have intercepts. We have an x-intercept at -2, 0. All right, so we have an x-intercept right here. Notice that is on the horizontal asymptote. So this graph actually crosses its horizontal asymptote. And we have a y-intercept at 0, negative 1/4. Right in there. Now, also recall that when we've talked about rational functions, when we talked about these last time, that the vertical asymptotes break the graph up into branches. And so this graph has 3 branches. It has a branch sitting over here somewhere, left of that vertical asymptote at -4, so that's branch 1 right there. And then there's a branch between the two asymptotes. That would be branch 2, sits in there. And then finally, there's a branch sitting over here to the right of x equals 2, and that's branch 3. So when I call these branches, the graph literally has pieces to it. And this has 3 distinct separate pieces to this graph, separated by those vertical asymptotes. Remember that a rational function can never cross its vertical asymptote. The vertical asymptotes are places where there's a break in the domain in the graph. And so it's those asymptotes literally separating the graph into pieces. All right, now if you're unclear about where these branches go, then what you can do is you can kind of pick some x values and plot some points to get a better idea of what's happening. Now those two intercepts are stuck in there in branch 2. So if branch 2 is one that you're worried about, which would make sense, then in branch 2, I might pick another couple of x values. Like I might pick x equals -3, and I might pick x equals +1. And those might make sense to get a couple of more points in there. And so you're literally finding f of -3 in this function, and you're finding f of 1 and seeing what the y values are. So f of -3, I'm going to look at the factored form of the polynomial. That's -3 plus 2 over -3 plus 4 times -3 minus 2, like that. All I'm doing is substituting into that very top form that's factored for this function. So you get -1 in the top, and in the bottom you get 4 times -5. I'm sorry, you get 1 times -5, so you get -5, or you get +1/5. So the key there is that it's positive, and since it's positive, it means that the point's a little bit above the axis. So it's sitting like right in there somewhere. F of 1. We have 1 plus 2 in the numerator over 1 plus 4 times 1 minus 2. So I get 3 over 5 times -1. I get -5. I get -3/5. A little bit past it, a half. So you get a point right about in there. And so those points are giving you a pretty good idea that this middle branch has got to fit in between these two asymptotes like this. Remember, the graph's got to approach the asymptote, the vertical asymptote there. So the graph crosses through the horizontal asymptote there, gets really flat right in here, and then comes in like this. And so that branch, that middle branch, has got to sit like that. By the way, I'm going to flip the screen for a minute. I'm going to come back to this one in a minute. But middle branches there, when I say middle branches, I'm talking about branches on rational functions that sit between two vertical asymptotes. There's really only a couple of ways that these could look. You could have a branch like the one we just did. Here's two vertical asymptotes that sits in here like this. It crosses through and goes like that. You have a falling branch like that. You could have a middle branch that is the same kind of branch, but a rising branch instead, and fits in between the two asymptotes like that. And there's a couple of other ways it could look. There ends up being 4 different ways that you could get that middle branch to look. It could look more like a parabola. Now, it may not be, it's probably not going to be symmetric. So you get a shape that looks maybe something like that, or a similar shape but upside down. And the graph may or may not have intercepts in there, possibly, but looks something like that, one of those two right there. Those middle branches are going to be one of those 4 shapes, basically. And so once you've got a couple of points, you should be able to figure out what the middle branch is going to look like. All right, so there's our middle branch on the graph. Now the 2 outer branches, so branch 1, if you are not sure that you know where branch 1 fits, and remember, you do have a graphing calculator that you can use to help, certainly, with this. But branch 1, if you're looking for a point, x equals -5 might be a good point to pick. And this branch 1 can only really look like this. It either sits above the horizontal asymptote or it sits below the horizontal asymptote. It's got to be one of those 2 shapes, basically. And so you're just trying to decide which one, whether it's above or below, pretty much. So we look at f of -5, and we get -5 plus 2 over -5 plus 4 times -5 minus 2. And so that gives us -3 in the numerator, and in the denominator, I get -1 times -7, so that's +7. And so you get -3/7 for that branch over there at branch 1, or for that point. So you have -5, -3/7 might be like right about there. And so that 1 point really tells you that this branch has got to be sitting below the horizontal asymptote. It's got to be sitting down there like that. That would have to be where that one is. And then finally, branch 3. So let's see, trying to put these in a different color so you can pick them out a little bit easier. They don't run together. So branch 3, an x value that might be a good x value to pick might be x equals 3. So you look at f of 3, and you get in the numerator 3 plus 2, and in the denominator you have 3 plus 4 times 3 minus 2. So you get 5 in the numerator. In the denominator you get 7. You get 5/7. And so that last branch has a point that sits over here at 3 5/7, like right about in there. And so that point, and again, one thing I didn't mention here, but again, this branch 3 could either be sitting above or below the horizontal asymptote. It's got to be one of those 2 shapes. And so that point being above the x-axis tells you that last branch has got to be sitting up here like this. Something like that. So this is a pretty complicated version or example for a rational function, but it's pretty typical, and it allows us to walk through a bunch of different things about these graphs. Also, don't forget that you're going to have a graphing calculator to help you with this, so that would be of help as well. this problem that I just sketched right here is probably a little bit more complicated than you're going to see on the exam. As far as, but please look at the exam review to get a pretty good idea of the kinds of problems that I'm going to ask for rational functions. Okay, so for those of you who are with me this morning, did anybody have any questions about anything I did on that problem?
No, I'm good with that.
I'm fine.
Okay, that's awesome. That's awesome. All right, so this finishes rational functions. And so we are now going to move on. Our next goal here, our next goal is exponential and logarithm functions. Like I mentioned at the very beginning of class, exponential and log functions. These are major classes of functions that if you're going to use mathematics later on. So anybody out there who is a math or science major of some type, a business major where you have to go on and take business calculus, anybody who has to take calculus in any way. So that's a lot, believe it or not, a lot of different majors, from biology to chemistry to math to computer science. All those people, geology majors, business majors, like I said, all of those majors have to go on and take some type of a calculus class. And exponential and logarithm functions are an important class of function in applications of mathematics. Both of them are, and the deal is that these functions end up being inverses of each other. Exponential functions and log functions are inverses. But see, the deal is, if you don't know what inverses are, then there's no way you can talk about exponential and logarithm functions. So that's one thing we have to do, is we have to talk about inverses. So before we can get to our goal of exponential and log functions, we've got to talk about inverses. However, to talk about inverses, you have to know something about function composition. And so we have to take 2 steps back before we can talk about exponential and logarithm functions. So we have to talk about function composition and combining functions. After we do that, we can talk about inverses. After we talk about inverses, then we can talk about exponential and logarithm functions. So combining functions and function composition is what we need to do today. So combining functions basically is what we're talking about. Now, function composition, and by the way, in your textbook, this is back in section 3.4. That's a section that we skipped earlier in the semester. And this is why we skipped this, because we didn't really need it until now. So, all right. So combining functions, it turns out that there are several ways you can combine functions. First of all, you can combine functions just using arithmetic. So what that means is, if you're given functions f of x and g of x, you can combine those by simply looking at arithmetic. When I say arithmetic, I'm literally saying you can take these 2 functions and you can combine them using addition. And you can form this function. The function's name is f plus g of x. And f plus g of x is just defined to be f of x plus g of x. In other words, you can take 2 functions and combine them to make a third function by just taking the 2 function equations and literally adding them together. It's all you're saying. Okay. All right. So you can take 2 functions and combine them by adding them together. F minus g of x is another function. You can take 2 functions and combine them by subtracting them. This is what I'm talking about with arithmetic. And then there's fg of x. That function is formed by taking 2 functions and multiplying them. So you get f of x times g of x. And then finally, f over g of x is formed by taking the 2 functions and literally dividing them. And so that all makes sense. You can form another function, a third function, by be given two basic functions by simply adding them, subtracting them, multiplying them, or dividing them. Now, there are reasons why you might want to do something like this, like you might want to use an arithmetic operation like this and combine two functions. So, as an example, if you had in business, if you have a function that is called the cost function. The cost function is sometimes labeled C of X, and a cost function is the costs incurred. In manufacturing something, right? Whatever we're talking about. And that the costs incurred in manufacturing might not be actually building it. It might be storing it. It might be transporting it. It might be the insurance that's required to store it. All sorts of things that are incurred. It's costs that are incurred for whatever you're trying to sell. And then you have another function that's called the revenue function. The revenue function is sometimes labeled R of X. And that is the money that you bring in from the sale of something, right? So C of X are the costs involved in whenever you're trying to sell. The costs for manufacturing it, the costs for storing it, costs for insuring it, all those different things that come into play. The revenue is the money you got coming in. So cost is the money you got going out. Revenue is the money you got coming in. But if you're in business, what you're interested in is you are interested in those two functions, but ultimately, what are you interested in? You're interested in profit. And so we have what we call a profit function, P of X. And that's how much money you're making, the profit you're making from the sale of X items. That one's an easier one to understand, probably. But how is the profit function connected to the revenue function and the cost function? Anybody who's listening right now, live, do you want to make a guess? How is the profit related to the first two functions, the revenue and the cost?
Revenue minus the cost.
Yeah, right. That's right. Profit is just the subtraction problem. It's just the revenue function minus the cost function. It's the difference between those two. But that's my point here. My point was to start this is, remember, on this previous page I wrote that you could take two functions and you could form a third function from those two by either adding them, subtracting them, multiplying, or dividing them. And so now what I'm trying to get you to see is that there are some situations where that would make sense. And actually taking two functions and adding, subtracting, multiplying, or dividing might actually give you a function that actually means something. So this is a problem where subtraction actually means something, right? Where you actually take two functions and you subtract them and it means something. It means profit in this case. So there's a reason why you might want to take two functions and subtract them. Then the revenue, you have another function that's sometimes called little p of x. Little p of x is the price function. And the price function is how much you're charging per item. And notice it's a function. So a lot of times it's a function because the price certainly that you might charge for an item is changing over time. And it may depend on how many items that you're selling. So that's the way I've written it right here. But the price function is connected to revenue. Revenue, remember, is the amount of money you got coming in. And so how is revenue formed? Well, it's formed by taking the number of items you sell, which is X, and multiplying it by how much you're selling them for. It's the number that you're selling times the cost per item. right? And so X is the number that you're selling. And little p of X is price per item. And it makes sense if you take the number you're selling and multiply it by how much you're selling them for. What are you doing? You're getting the revenue. You're getting the amount of money that you're bringing in. And so what do we have here? We have a situation where it makes sense to take two functions. In this case, it's X and the price function, P of X, and multiply them, right? So multiplication gives you something that is usable, right? In this case, revenue. It's a piece of information that you might want. So multiplication is an important operation here. So I'm just trying to I gave you two examples of situations where it makes sense to either add, subtract, multiply, or divide two functions. All right, so now let's go through and actually do that, and not with any function that has any in particular meaning, by the way, just so that we can go through the process. So let's say we have f of x is 2x squared minus 1, and g of x is 3x plus 4. Right? Then those four functions that I just outlined, you have f plus g of x. And how is that defined? That's just f plus g. So that's just 2x squared minus 1 plus 3x plus 4. And literally all you do here is you add the like terms together. And so f plus g of x would be 2x squared plus 3x plus 3, right? And so what did we do? We took two functions that were basic functions in this case, kind of like building blocks, 2x squared minus 1 and 3x plus 4, and we formed a third function by taking those first two functions and adding them together, right? So we're forming a third function from two given functions. All right, f minus g of x would be the f function minus the g function. So it'd be 2x squared minus 1 minus 3x plus 4. And you'd have to put the 3x plus 4 in parentheses there and make sure that you deal with the signs correctly. So you'd have 2x squared minus 1 minus 3x minus 4. And so f minus g of x would be our function 2x squared minus 3x minus 5. Right? That would be a different function than the first one that we formed, certainly. And so what do? We took two functions, we subtracted them, we formed a third function. fg of x, you get that by taking the two functions and you multiply them. So you have 2x squared minus 1 times 3x plus 4. And in this case, to multiply them, I would just use the FOIL method to multiply that out. You get 6x cubed plus 8x squared minus 3x minus 4. And so that would be our function fg of x. Be 6x cubed plus 8x squared minus 3x minus 4. All right, and then finally f over g of x, the division function. We'd have 2x squared minus 1 over 3x plus 4. And in that case, remember that when you have a fraction, you get a restriction in the domain. And in this case, x cannot be negative 4/3 because that would give you 0 in the denominator. But other than that, there's not really anything different. So you get that is our division function. F over g of x would be 2x squared minus 1 over 3x plus 4. And in this function, x could not be negative 4/3. Right, because that would give you 0 in the denominator of the function. So there's an extra little tiny restriction at the end on that problem. All right, so it's really that simple to calculate this. Now, the other thing that you should be aware of with these addition, subtraction, multiplication, and division functions is that if I gave you two basic functions, so this is a different example now. If I give you f of x is let's say the square root of x plus 1, and g of x is the absolute value of x minus 3, like that. And I asked you to find, let's say, fg of 8. Fg of 8. So in a problem like that, you're not actually creating the function, you're just trying to calculate a value. And so you use the definition for the multiplication function. Fg of 8 is defined to be f of 8 times g of 8, right? That it's the multiplication function. So you're just taking both f and g and you're evaluating them at 8 and then calculating the result. So f of 8, what's f of 8 equal to? That's underneath, this is the square root of 8 plus 1, or the square root of 9, or 3. So f of 8 is 3. And then g of 8 is the absolute value of 8 minus 3. And so that would be the absolute value of 5, which is 5. And so fg of 8 would be equal to 15. You just multiply those two results together, right? So that's all you're talking about if you're actually trying to calculate a specific value for functions like this. You're not actually trying to create the function. You're just trying to calculate a specific value. All right. Now, there is another way to take two functions and combine them. And that's not the way I'm outlining any of these right here. There's another way to take two functions and combine them is not with arithmetic. And this is with what we call function composition. And function composition has a symbol just like addition has a symbol, right? Addition has this symbol, that it's a plus sign, right? And that's the that's telling you to take two functions and add them together. Well, function composition has a symbol also, and it's an open circle. And it makes a difference which way you actually put the order of the functions. And so you get different answers depending on which way you do this. And so you actually have two ways you can compose two functions. Now, I just read these either as f circle g of x and g circle f of x, or I read them as f composed with g and g composed with f. Either way, you'll see it read both ways. And obviously, some students say fog and goff, but it's not really an O between the two. It's really just an open circle. The f circle g of x is defined to be f of g of x. And g circle f of x is defined to be g of f of x. These are functions of functions. That when you're taking two functions and composing them, you're talking about taking a function of a function, is what you're doing here. All right, so let's just look at calculating values first of all. So let's say I have the function f of x is x squared plus 3x minus 1, and g of x is x plus 2. All right? And I want to calculate f circle g of 2. So f circle g of 2, by the definition that I just wrote at the top, is defined to be f of g of 2. That's f circle g of 2, f of g of 2. And so what is that saying to do? That's saying you're going to take g and evaluate it at 2, and then you're going to take f and you're going to use that for the answer. A nice little picture. Well, let's actually do the calculation here first. So what do I do first? I do the inside first. I do g of 2. So g of 2, based on the definitions, is 2 plus 2, or 4, because g of x was x plus 2. So this becomes f of 4, right? G of 2 and 4 are the same thing. And then f of 4, you just evaluate f of 4 like you would typically do, substitute 4 in for x, and you get, what's f of 4 here? It's going to be 16 plus 12 minus 1, and you get 27. So f composed with g of 2 is equal to 27, right? And now drawing a picture of this, I think sometimes helps make a little bit more sense of what we're doing here. I mean, you start with 3 circles here, and what's the x value we started with? We started with 2. And what was the function that operated on 2 first? The function that operated on 2 was g. That was that inside function. And g took 2. There's g right there. It took 2, and it took 2 to 4. And then after we calculated that, then f took over and took 4, and it took it to 27. And so f took over after that. So this picture helps illustrate the idea that we're not operating with both of those functions at the same time, that we're first operating with g, calculating something, and then we're operating with f, and then calculating something from the answer there. And what does f circle g of x do? F circle g of x goes straight from 2 to 27. So this is f circle g right here. Right, it takes 2 directly to 27. All right. Let's look at g circle f, g of f of negative 1. So by definition, this would be g of f of negative 1. Right, that's how we would define this. And then this says, what do we do first? We calculate f of negative 1 first. So f of negative 1, remember what our original functions, here are our original functions. I'm putting these in a box right here. So f of negative 1 would be 1 minus 3 minus 1, or negative 3. And so this is g of negative 3. And then I calculate g of negative 3. G of negative 3 is negative 3 plus 2, or negative 1. So g composed with f of negative 1 would be negative 1, as it turns out. You happen to get the same value back. You can even take a function and you can compose it with itself. Looks kind of crazy, but definitely something that can be done. So, like, for example, we could have f composed with f of, let's say, 4. F composed with f of 4. And so by definition, this would be f of 4. And so f of 4, you do the first one, and f of 4 would be equal to 16 plus 12 minus 1, or 27. So this would be f of 27. And we had calculated f of 4 at the top of the page before. And then f of 27, well, that one unfortunately would be a little bit bigger than I had anticipated. That's 27 squared plus 3 times 27 minus 1. And so 27 squared is, I'm going to get my calculator out here real quick because I'm being lazy. So 27 squared is 729, which actually I should have known. Plus, and then 3 times 27 would be 81 minus 1. And so you get 809 when you do that. 809 right there. So f composed with f of 4 is equal to 809. All right, so that's how you calculate specific values for composition. So that's one thing I wanted to look at with composition. Another thing I want to look at is if you are given 2 functions. So let's say I have f of x is 3x minus 4 squared. 3x minus 4 squared. Sometimes you'll see this written out as decomposing a function. Not composing it, but decomposing. So can you take this function and rewrite it as the composition of 2 functions? can you write it as that f of x is g of h of x, right? Is the way to look at this. And this is actually not hard to do. H of x is simply, the way I look at this is what we call the inside function, and g would be what I would call the outside function. And so the inside function here is 3x minus 4. H of x is 3x minus 4. And then the outside function, what are we doing with 3x minus 4? We're squaring it. So the outside function is the square function. And so g of x would be x squared. So now watch what we can do here. If you took these two functions and you looked at g composed with h of x, g circle h of x, which is g of h of x, the g function of the h function. So then the h function is 3x minus 4, so this would be g of 3x minus 4. And then you go to the g function, and every place you see an x, you'd substitute 3x minus 4, and sure enough, you'd get 3x minus 4 squared. And so this is decomposing a function. This is our original function right here. And what we did is we wrote it as the composition of two smaller functions. In this case, g of h of x, the square function of the 3x minus 4 function. All right? It takes a little bit of practice to get used to doing this, where you're decomposing a function like this. But let's look at another example. Let's say we have the square root of x cubed minus 1. The square root of x cubed minus 1. So in words, what is this? This is the square root function. The square root function of the x cubed minus 1 function. So what would be the inside function here? The inside function would be our x cubed minus 1. That's our inside function. And the outside function would be the square root function. That would be our outside function. And so if you're going to try to write this as g of h of x, remember g of h of x is really just another way of writing g circle h of x. Those are the same function. But if thinking of it as g of h makes it a little bit easier here, because you can see the inside function and the outside function. So the inside function here would be x cubed minus 1. And the outside function, that would be our g function, would be the square root function, be the square root of x. Right? And that would allow you to write it as a composition that way. All right, let's do one more like that, where we decompose it, and then we'll actually look at composing some functions, and then we'll be done. All right, so let's say I have f of x is the absolute value of x to the 4th minus 10. So this would be, if you're going to think of this as g of h of x, right, the inside function in this case would be the x to the 4th minus 1 function. That would be my inside function. And then the outside function would be the absolute value function. This is the absolute value function of the x to the 4th minus 10 function. And so my inside function, h of x, would be x to the 4th minus 10. And my outside function, g of x, would be just the absolute value function, the absolute value of x, like that. And you could always just go through and calculate this and make sure that what you've got is right. So the g of h of x, right, replace h of x with what it's equal to, which is x to the 4th minus 10. So this would be g of x to the fourth minus 10. And then that says go to the g function, and every place you see an x, substitute x to the fourth minus 10. And so I put the x to the fourth minus 10 into that absolute value function, and I get the absolute value of x to the fourth minus 10. I get exactly what I was looking for. And so this is decomposing it, right? This is my original function right here. F of x is the absolute value of x to the fourth minus 10. And this is how we've decomposed it into two smaller functions like this. Now, you can't always do this, but there's some functions that are set up the way they're written. They're set up so that you could do this. All right, let's finish class today then. Not with decomposing two functions. Let's compose functions now. So actually composing some functions, not calculating values, not decomposing functions into its two smaller pieces, but taking the two smaller pieces and actually composing them to create a bigger function, to create a composition function. So let's say I have g of x is, excuse me, is 3x squared minus 4, and f of x is 2x minus 3. All right, so if I look at the composition here, so I would look at two different compositions. I have g composed with f of x. I'm creating that function here. So I'm actually composing these two functions to create this. Then that would be g of f of x, write out the definition. So I write out the definition for composition. And then I calculate this composition here. So this would be g of f. F is 2x minus 3, right? So in place of f, I'm going to highlight it here. There's f on the inside there. And what did I do? I just replaced f with what it's equal to. So f and 2x minus 3 are the same thing. So that's all I'm doing. And then what does this tell me to do? This says go to the function g, and every place you see an x, you're going to put a 2x minus 3 in its place. So what I do is I actually write the function g. Now look at the way I'm writing it. I'm writing it, there's my function g, but in place of the x, I put just an open set of parentheses. And then what are you doing? You are replacing in that open set of parentheses, you're just substituting or parachuting in that 2x minus 3. What are you doing? You're putting the 2x minus 3 function into the 3x squared minus 4 function. And so you get 3 times 2x minus 3 squared minus 4. And then I would do the arithmetic there. So that would be 3 times 4x squared minus 12x plus 9. When you square that out, that's what you get. And so that gives me, that gives me 12x squared minus 36x plus 27 minus 4, or 12x squared minus 36x plus 23. And that would be my composition function. That would be g composed with f of x, right, when you do all the arithmetic. All right, so what is g of f of x? G of f of x is, you write out the definition. So here's my definition right here. Put the box around it. That's the definition for g, circle f. It means g of f of x. And then you start on the inside piece. The f of x, you replace it with 2x minus 3. And then that tells you to go to the g function, and every place you see an x, you're going to substitute 2x minus 3. And there's my 2x minus 3, and it's going in place of the x that was, that's in g of x there. All right, now we can do the other composition the other direction. This one's not going to require as much algebra, so I do have enough room for it here. So in this one, we would be looking at f composed with g of x. So f composed with g of x would be f of g of x. So write out the definition. And then what are you doing? You're looking at the inside functions. I'm looking at g of x, and g of x is 3x squared minus 4. So you replace g of x with what it's equal to. And so here's g of x on the inside, and what did I do? I replaced g of x with what it's equal to, which is 3x squared minus 4. And now I go to the f function. I write down the f function, because this is f of 3x squared minus 4. So this is saying go to f. Every place you see an x, you're going to put in 3x squared minus 4. So here's my f function. But notice what I'm doing, again, is in place of the x in the f function, I'm putting an open set of parentheses. And what are you going to do? You're going to parachute this 3x squared minus 4 into that open set of parentheses. So you put the 3x squared minus 4 in place of x right there. I'm just doing that as two separate steps so you can see that that's what I'm doing. You wouldn't have to do that necessarily. So that would give you 6x squared minus 8 minus 3, or finally 6x squared minus 11. And that would be f circle g of x right there, like that. Okay, anybody, are there any questions from anybody there? I don't hear any questions, so I think we're okay. Okay. So let's look at a different kind of group of functions. Let's say we have f of x is 1 over x, and g of x is x plus 3 over x minus 2. All right, so this one's going to be a little bit trickier as far as looking at composition, because you've got these fractions here. So you have f circle g of x is f of g of x. You write out the definition. And then in place of the g, what do? I substitute what g is equal to, and g is this function x plus 3 over x minus 2. It's a rational function. And so once again, here's g of x. In place of g of x, I put what it's equal to, which is x plus 3 over x minus 2. Now this tells me to go to the f function, and the f function is 1 over x. So I'm going to follow exactly like I did in the last couple of problems. Every place I see an x, I just put this open set of parentheses. Now there's just 1 over x, so it's 1 over this open set of parentheses. And so what do you get? 1 over, and I plop that x plus 3 over x minus 2 in the place of the parentheses there. And so I get 1 over x plus 3 over x minus 2. So that's 1 divided by that, which is just means you're multiplying by the reciprocal. So you just invert and multiply here, and you end up with x minus 2 over x plus 3. And so that's my composition function. So that's f circle g of x is equal to x minus 2 over x plus 3. Now these functions have all sorts of restrictions on them when you've got composition like this. When you have fractions, you know, the first one, the restriction was that x couldn't be 0. The second one, the restriction is that x can't be 2, because remember, you can't have 0 in the denominator. And then, so those restrictions kind of, in some ways, carry over to this last function. And notice this last function also has a completely separate and new restriction that x can't be negative 3. There's other restrictions for f circle g as well that carry over. But we're just not going to get too involved in the restriction stuff here. Any more than what I just did right there, because it starts getting really kind of complicated to look at the restrictions on these composition functions, especially when you've got rational functions here. And right now, the main thing is I want you just to be able to get through composing two functions. All right, so composing the other direction, you have g circle f of x, which by definition is g of f of x. And so we go to the inside piece there, the f of x, and this is g of 1 over x. Where I just replaced f of x right here, f of x with what it is equal to. And now I go to the function g, I'm putting my parentheses in here every place I see an x. So I get that expression right there, and then what am I doing? Every place I see an open set of parentheses, I'm plopping in this 1 over x. Like that. Now you end up with a complex fraction. I'm not going to get too crazy with complex fractions here, but to clear out the complex fraction, and you'd want to do that, you would multiply the top and the bottom just through by x. If you multiply the top and the bottom both through by x using the distributive property, first of all, that's legal to do because you're doing the same thing to the numerator and the denominator. You're multiplying both of them by the same thing. So you're really multiplying by 1, which is okay to do. But then when you use the distributive property here to multiply, the x's would cancel. And so you'd end up with 1 plus 3x over 1 minus 2x. And that would be the preferred form right there, is you try to get rid of those complex fractions if you can. And there's my composition, 1 plus 3x over 1 minus 2x. All right, so that's another example of creating these composition functions. The last example I want to look at, let's say I have g of x is 2x plus 3, and f of x is x minus 3 over 2. All right, so when you look at the composition here, I want you to see what happens in this problem. And this one's actually going to be easier than the ones we've just been doing. This is g of f of x. So this is g of x minus 3 over 2. And so I go to the function g. Every place I see an x, what am I going to do? I'm going to plop in this x minus 3 over 2. Right, and it's the 2x plus 3 function of the x minus 3 over 2 function, right? You're plopping in the x minus 3 over 2 function is getting put into the other one, right? I'm putting the f function into the g function here. So the 2's divide out here, and notice you get x minus 3 plus 3, and you end up with just x as the answer. So g composed with f of x is just equal to x. And if you, kind of draw a picture out here for this example, notice I only put 2 circles as opposed to 3 circles like we did before, and watch what happens. We start with x. The function that started with x in this problem, this is this inside function, would be f. And f takes x to f of x, right here. But then what function takes over? It's g, and then g takes f of x, but notice where g takes f of x. It takes it, what was the answer to our calculation right above that picture there? It was x. So g actually takes f back to x, like this. And if you look at those 2 arrows, you're getting here that f and g are doing exactly the opposite thing. F and g are inverses of each other. This is what we're going to explore in class next Monday, in lecture on Monday, is this idea of what happens when you have 2 functions that when you compose them, you get x. By the way, notice that if I compose them in the other direction, I get f composed with g of x, you get f of g of x, and so that would be f of 2x plus 3, right? The g function and the 2x plus 3 function are the same. And I go to my other function, the f function, and in place of the x, I put 2x plus 3. And notice what happens. The 3's cancel, and you get 2x over 2, or just x. The other composition's x also. Now, this isn't always going to happen, by the way, but most of the time it does. And for most normal types of functions, when you compose one way and you get x, you're going to compose the other way and you're going to get x that way also. All right, so this is kind of leading into what we're going to be talking about in class on Monday in Monday's lecture. All right, so textbook homework on inverses, or I'm sorry, on composition function, textbook homework. And this is on page 218 of your book. And on page 218, I was hoping I could get you to look at problems 5 through 17 odd. Really not too many problems there. And then 27 through 41 odd. Okay, so those would be good practice problems on composition and combining functions. Remember, that's kind of where exam 3 is going to begin. So remember that I have online office hours this evening from 8 to 9 o'clock. So take advantage of that. I have, in this class, I also have online office hours tomorrow on Thursday from 11 to noon. And then again on Sunday from 7:30 to 9 o'clock in the evening. Remember, I'll be on campus next Tuesday and Wednesday. Remember that the exam 2 review is up, and it's a really great review. Lots of problems on there. It's a lot longer than your actual exam, but that's a good place to start working on getting ready for exam 2. So if there are no questions from anybody who's watching right now live, I don't know if are there any questions from anybody?
Beer.
All right, so then everybody have a great day. Come by my office for help if you need it. Start getting ready for exam 2, and I will be in touch with all of you soon. Look for emails from me pretty soon also about next week's exam.